the last file. If for any reason we have a trouble with this PC, you can rest 10 minutes. If for any reason I'll disappear, and you can rest 10 minutes because I will turn on another PC if in case of troubles, but I hope there are no troubles. Okay, so let me share my desktop. Ok. No, questo no. So you need to take Crash Course of Mathematics, the last file, linear algebra. Again, if you don't hear, if you have troubles, if you have questions, you can stop me. You can turn on your microphone. Okay, you can turn on your microphone and talk whenever you have troubles. So guys, today we start a new topic of mathematics, which is linear algebra. In particular, we are going to talk about the definition of vector, of matrices, operation between matrices, and the notion of determinant, the property of the determinant, the inverse of a matrix. We will see, because today we have the last 3 hours, so we will see what we can review about these topics. So as always, first I will review, I hope quickly, some definitions, some property of matrices. Then we are going to review everything with some examples, okay, with some exercises. So don't be scared. So this is a vector V. I denoted it with an arrow. You see, with this arrow, a vector V with n components is an ordered set of n numbers. And this is the notation used to denote the vector. And these are, yes. Yes.
We can see what you are displaying.
Oh, thank you, guys. You are not able all to see. No one is able to see.
No, I can't.
No.
Oh, okay. So I go out. Okay, guys. Sorry. Thank you, guys. I share it again. I hope today team has. I hope now it's to work, but let me see. Problem of with team. Let me share my desktop again. Again, please. If you don't see, let me know. Now I shared again my desktop. You know that when this occurs, sometimes you have to close it several times. Do you see it now?
Yes.
And now you see. I hope. Thank you, guys. So a vector V with n components is an ordered set of n numbers and is denoted in this way. This is specifically called column vectors. And these are the element of the vector. They are ordered in the sense that the element 2 of the vector is this one, the element 1 of the vector is in this. Yes.
We see your team dashboard, so you should switch to Microsoft Edge to the browser. Oh, okay. Thank you.
Don't you see?
Now it's okay.
Okay.
Thank you.
Thank you. Thank you. Thank you. So this is a column vector. In particular, okay, this is a column vector. Or if you want, you can see below, write the dimension of the vector is n times 1. You can write it below this V to say that you have n1 rows and 1 column, n rows and 1 column. So this is a vector of dimension n times 1. This is a column vector. A matrix of order n times n, m, is a table of doubly ordered numbers with n rows, 1, 2, 3, n rows, and m columns, 1, 2, 3, etc., m. We denote as Aij the element of A in the ith row and in the jth column. So you can find and identify every element of this matrix by specifying the first number here, which denotes the number of the row, and the second element, which denotes the column. For example, A2M is the element in the second row and in the M column, the column number M. AN2 is the element in the row number n and in the column number 2. So column, row and column. So this notation of matrix. So this matrix has dimension, you can write it below the matrix, n times m, which means n rows and m columns. So a column vector, like the one we described before, is a special case of a matrix. Is a matrix with n rows, but only with one column. Okay. A square matrix, in particular, is a matrix for which the number of rows is equal to the number of columns. So a 3 times 3 matrix, a 4 times 4 matrix, a 5 times 5 matrix are examples of matrices which are called square matrices. Guys, these are simply definition, and don't be scared because we will review them with exercises. First, I need to finish to tell you some of the definition properties. Now, the sum between two matrices. So suppose you have a matrix A and a matrix B. These two matrices have the same order, n times m. So this is an n times m matrix, and this is an n times m matrix. So I'm saying that these matrices have the same order, or in other terms, they have the same dimension. The matrix C, defined as the sum of the matrix A and B, is the matrix such that its element ij in the ith row and the jth column, denoted as Cj, Cij, is simply obtained by summing the elements of the matrix A and of the matrix B in the position I and J. So the sum is very easy. It's made up by summing each element of the matrix A and of the matrix B on the same row and the same column. So you see Cij, Aij, Bij. But I told you, we'll see how easy it is with the examples. Okay, now here I'm simply add that now. You can skip it, not a stupid note. Well, A plus B, look at this one, A plus B is equal to B times plus A. So the commutative property, 2 plus 3 is 3 plus 2. This property, the commutative property that holds
Professor, we can't hear you anymore.
Sorry, guys. I needed to change PC. I don't know why I had the problem. Are you still here? I'm back.
Yes, we are here.
Yeah.
Yes, we are here.
Now I open again. Thank you, guys. I'm sorry. I share again my desktop, and I first of all try to find my file again. So we are Crash Course of Mathematics. Wait, I tell you, and where is? Now I need to find the file linear algebra. Sorry, this is open, and in the meanwhile I share my desktop also. Okay. Sta succedendo qua? So guys, we were talking about matrices and vectors, and in particular we started by talking about the sum of matrices. The conclusion was the following. In a moment I go to the slide. The conclusion was the following, that the sum between matrices is feasible if and only if the dimension of the two matrices that you are summing, that is matrix capital A and matrix capital B, have the same dimension. This means that the number of rows of the matrix A and the number of rows of matrix B must be both equal to n, and the number of columns of matrix A and the number of columns of matrix B must be m, and the result of the sum between two matrices is a matrix called, for example, C, which has the same number of rows of A and B, that is n rows, and with the same number of columns, which is m. Mamma mia, dov'è? So, okay. I hope okay. So, let me see. Time. Sorry, guys. So, now, another operation that we need to see is the product of a matrix by a scalar. Let me see. Product by a constant. It's very easy to make the product between a matrix of every order and a scalar k. Scalar k means simply a number. You can always do the product between a matrix and a number, and the result is simply another matrix having the same dimension of A, whose elements are all equal to the elements of your original matrix A times K. So in particular, the element A, I, J of the new matrix is equal to A, I, J, which was the element A in the ith row and the jth column of A, times the constant K. So it's very easy. You have simply to multiply all the elements of the original matrix capital A by the number. That number, the constant, is a given number. Another operation between matrices is the product. Guys, let A means, I tell you what does this mean. This means that A belongs to the space of the matrices of order m times n. Simply, let A be a matrix of order m times n, m rows and n columns. And let B, capital B, be another matrix of order n times p, that is with n rows and p columns. Then their product is a matrix, I called it C, the product, which is A times B, okay? and this means is a matrix of order m times p. That is a matrix having, look, the same as a row, the same number of rows of matrix A, which is the first one here, and as a number of column, the number of column of matrix B. You see, m times p. And in particular, guys, I will show directly with the example how to make the product. And in particular, the product is, I wrote everything below, is feasible if and only if this number and this number are equal. But this number denotes the number of rows of the first matrix, the number of columns of the first matrix of A. This number denotes the number of rows of B. So the product is feasible if and only if the number of columns of the first matrix is equal to the number of rows of the second matrix. And the result is a matrix with a number of rows equal to m, the number of rows of the first matrix, and with the number of columns equal to p, the number of columns of the second matrix. In particular, as I will explain by showing the example, guys, the element ij of the product is obtained by multiplying, by doing a product that I still have to explain, by multiplying the ith row of the matrix A with the jth column of matrix B. In fact, this is called the row product. The product between matrices is called row column product, but I will explain it. Okay, so don't be scared. We will see everything. If you don't remember, don't be scared. Okay, so for a moment, what I want you to remember is that the product is feasible. You can do the product if and only if this number is equal to this one, and the result is the matrix of dimension m times p. Okay. And an important observation is the following. Contrary, while for numbers, you have, for example, that 2 times 3 is equal to 3 times 2, which is 6. For matrices, in general, A times B is not equal to B times A. In particular, it can happen that A times B is feasible, but B times A is not feasible. It can occur that A times B is feasible, B times A is feasible, but what you get are different matrices with different elements. And why? Because you have to think to the definition of the product I told you, that the result is a matrix of order A times B is feasible if and only if this number is equal to this one. So if you do, for example, B times A, your first matrix is B. Okay, your second matrix is A. So the result is feasible. I mean, the product in this case is feasible. The product B times A is feasible if and only if P is equal to M. Suppose that P is equal to M. If P is equal to M, the product is feasible. But the result is a matrix of dimension n times n. N times n. So in general, yeah, you can, yes, I wrote everything here, guys. I simply told you what I wrote here. Let A be, what does this mean, guys? N times n means that A is a matrix of a square matrix, and let I be a matrix of order n. Again, so this is a square matrix, and this is also a square matrix. But what I'm saying in reality is more general. However, for simplicity, I explain it for square matrices. The matrix I, which is a matrix with all diagonal elements equal to 0, all the diagonal elements equal to 0, all the diagonal elements equal to 1. I'll show, okay, guys. All the diagonal elements equal to 1, and all the element outside to the main diagonal equal to 0 is called identity matrix. In particular, if you do the product, can you do the product between A and I? Yes, because you see, this is a square matrix of order n. This is a square matrix of order n. So you see this n obviously is equal to this one. So the product is feasible. Then the result is a matrix of dimension, the number of rows of this one times the number of rows of this one. The identity matrix, guys, so if you do this product, you get that A times capital I is equal to I times capital A, and which is equal to A. So what I'm saying here, I told you, in general, the product A times B is different from B times A if they are both feasible, okay? Supposing that they are feasible, okay? But I is a matrix such that if you multiply A by I is equal to I times A. So in this case, the product is, how can you say, commutative? I mean, you can exchange the order of the matrix, and the result is the matrix equal to A. So the identity matrix, guys, plays in general, not only for square matrices, but also for other matrices, the same rule played by the number 1 when you talk about product between numbers, which is the result of 3 times 1, guys. 3 times 1 is 3. 1 times 3 is 3. So 3. So the identity matrix plays for matrix the same rule that the number 1 has for in the product between numbers. So in other terms, 1 is the neutral element of the product for numbers. The identity matrix is the neutral element of the product for matrices. In particular, guys, here I explain better which is the meaning of matrix A, of matrix I. First of all, observe the matrix I is a square matrix because the number of rows is equal to the number of columns, okay? And another important thing is the following. All the elements of the main diagonal are all equal to 1. Which are the element of the main diagonal? A1, 1, first row, first column, A2, 2, second row, second column, A3, 3, third row, third column. All these elements such that the index of the row is equal to the index of the column are elements belonging to the main diagonal. So all the elements for which the number of the row is equal to the number of the column must be equal to 1. So all these elements must be equal to 1. So an identity matrix is a matrix such that all these elements, the main diagonal, are equal to 1, and all the other are equal to 0. So for I different from J, so this index is different from this one, then the value is necessarily equal to 0. So, and here, okay, I repeat, I wrote everything. Let me tell some things, and then we will see application directly. Now, transposition is an operation. Here you can suppose you have a matrix A. What does this mean? This means belonging to the space of all the matrices with n rows and n columns. So essentially, this means let A be a matrix with n rows and n columns. Then this matrix that you read as A transpose is a matrix with the number of rows equal to the columns of M, and with the number of columns n, which is equal to the number of rows of A. This is called, I repeat, the transpose of A, and its elements are simply obtained by exchanging the rows of A with its column. Exchange the row of A, which are n rows, with the columns, and you get the matrix A transpose. I will show it graph with numbers, okay, in a moment. I need to finish some definition, and then we will see everything with numbers, with matrices, so with real matrices, so you can see how everything is easy. So don't be scared for the moment if you have never seen this topic. Properties of the transpose. Suppose you have a scalar. K is a scalar. A scalar means a number. Well, a number, guys, can be seen itself as a matrix with 1 rows and 1 column. So the transpose of a number, for example, 3 transpose is still 3. So the transpose of a scalar is a scalar itself. If you have A transpose and you transpose it, obviously you get again A, because if A, guys, is an n times m, n, I do an example. Suppose A has a dimension 2 times 3. Transpose it. You get a matrix of order 3 times 2, because you exchanged the rows of A with its column. So I repeat, you have a matrix now of order 3 times 2. Exchange again the number of rows and column of A transpose, which was, I told you, a 3 times 2 matrix. You get a 2 times 3 matrix, which is obviously A again. If you have, this is called, guys, linear combination. If you have a constant that multiplies a matrix plus a constant that multiplies another matrix, assuming that A and B have the same dimension. I think I wrote it, otherwise, no, I didn't write it, but you know that the sum is feasible. Essentially, this is a sum, guys, because H times A means multiply all the elements of A by the constant H. K times B means K is a scalar, I repeat, multiplies all the elements of B by K. So the multiplication, so this means that this sum then is feasible if and only if the dimension of A is equal to the dimension of B, because the multiplication by a scalar does not modify the dimension of the original matrix. Okay, this is called linear combination, when you have a constant times a matrix plus another constant times a matrix is a linear combination of matrices. If you want to take the transpose, you can proceed in this way. You can do alternatively H times the transpose of A plus K times the transpose of B. So this result is the same. So what I'm saying that first you can either do the operation inside parentheses and then compute the transpose. Alternatively, you can first compute the transpose of A, the transpose of B, then do H times the transpose of A plus K times the transpose of B, and what you get is exactly the same matrices. Another important property, which is useful very often in econometrics especially, is the next one. Suppose that A times B is feasible as a product, because I told you it's not always feasible, and I told you when a product is feasible. Well, an important property is the following. If you have A times B transpose, this means that you can, let me say, this is equal to what? B transpose. So you have to start from the last matrix, transpose times A transpose. Okay, so you have to take the transpose of the last matrix times the transpose of this matrix. So if you have an operation like this, you can proceed in two different ways. Either you can compute first A times B, then you get a matrix, then exchange the rows of this matrix with its columns, and you get what required. Alternatively, you can first transpose B, then transpose A, and multiply B transpose by A transpose. So this is a very important property, especially in econometrics. You will use probably with the professor of econometrics to show some proof of some result. Here, guys, in a moment we have the last things, and then we have exercises. The last things, okay. Inner product or scalar product. And here I defined it. Inner product, given two vectors, V n times 1, we remember, is a column vector. You have n rows and 1 column. And the vector W with n rows and 1 column. So is a column vector with the same dimension of V. So given two columns vector with the same dimension, the inner product, also called scalar product, can be written in the following way, as, for example, V transpose as dimension, guys. What does mean V transpose? That you have to exchange the rows of V with its columns. So will be a vector of dimension 1 times n. Okay, 1 times n. So 1 times n means a row with n columns. So this is, if this is a column vector, then its transpose is a row vector because it has one row and n columns. VW is an n times 1. I'm asking you, I told you guys that a product, sorry, I told you when the product with matrices is feasible, but I also told you that matrices are vectors are special cases of matrices. Do you think that this product is feasible? Yes or no? Yes, it's feasible. Why? Because you have to look at this number, because this is a number of columns of V transpose. This n is the number of rows of W. They are equal, so the product is feasible, and the result is what? A matrix having as number of row the number of row of this one, which was 1, and as column the number of columns of this one, which is still 1. So which is this result? Which kind of matrix is a 1 times 1 matrix? Is a matrix with 1 row and 1 column. So it's simply a number. So this, when you have a vector like this times you have a row vector 1 times n times an n times 1 vector, then this product is called scalar product because, or inner product, and the result is a number. Alternatively, guys, for the scalar product, you have this property that instead of computing V transpose times W, you can first transpose W, so W transpose, which will be obviously a vector of dimension 1 times n, times V itself, which is n times 1. Again, 1 times n times 1 is feasible because n equal to n, and the result is a matrix of dimension 1 times 1, therefore a scalar. And in particular here you find the definition of a scalar or inner product. What you have to do simply, look at the sum. You have the sum from I equal to 1 to n of what? Vi times Vj. Please, write Vi, I don't want, please, here write I, typo, write I. What does this mean, guys? When I is equal to 1, what you have? V1 times WV1. So, times W1 plus V2 times W2 plus V3 times W3 plus etc. Vn times WVn. So how can you perform the scalar product? Simply you have to multiply the first element of this vector times the first element of this one, plus the product between the second element of this vector times the second element of this vector, and so on and so forth and so forth. I tell you only a property, two vectors. Guys, what does mean Rn? Two vectors, which is the dimension of this vector? N times 1. So is a vector of n real numbers. The same here. So when you have a vector, a real vector, n times 1, you have a set of n real numbers. So this vector, guys, and this vector, we say that they belong to Rn. Rn is the set of the vector, of the real vectors with n components. Its components must be a real number. As there exists R, which is the set of the real numbers, there exists also Rn, which is the set of all the vectors containing R real numbers. In particular definition, two vectors are said to be orthogonal if their inner product, this one, gives 0. Remember it as a definition because sometimes in econometrics you require that some vectors are orthogonal. Okay, guys, coming back for a moment and going then immediately to the exercise so you can see how easy are these concepts. Okay, now if you've never seen them, okay, you say, oh, what is it? No, don't be scared because they are very easy even if you know nothing about mathematics. Okay, so it's very easy. However, here obviously I was saying some concept, and if you've never seen it, you can say, oh, it's art. No, now I show you the exercise that are super easy. So I do some exercise only to see, to understand the meaning of the things I explained. Remember, essentially, here I told you, wait a moment before I finish to explain the meaning of product, how to compute the product between matrices. Here, remember, I told you the element Cij is given by this formula, but don't read it because it creates confusion. Cij is simply obtained by performing the scalar product, guys, the last product I just defined with you, between the row I of the matrix A and the column J of the matrix B. And this product, guys, is feasible because we are talking of a row matrix, the product is feasible because the row of the element of the, the ith row, guys, of this matrix A can be seen as a row vector. The jth column, the column J of the matrix B, is a column vector, and they have exactly the same number of elements. So the product is feasible. But don't be scared, guys. I go directly now to the exercises, so we review all the things we explained up to now. So with numbers, you can see immediately that there are no difficulty at all. For example, consider this data. Here I reported some matrices and a couple of vectors. Okay, talk with me. Which is the dimension of this matrix, guys? You have how many rows? These are the rows, 1 and 2. So you have 2 rows. How many columns? 1, 2. So this is a 2 times 2 matrix. So a square matrix of order 2. How many rows do we have? 2. How many columns? 3. So B is a matrix of dimension 2 times 3. So A is a square matrix, B is a general matrix, or if you want to add to say a rectangular matrix, but simply call it matrix. C again is a matrix of order 2. In particular, you have 2 rows and 2 columns, so it's a square matrix of order 2. Look at V. So you denote matrices with capital letters, and you denote vector with an arrow. Okay, or sometimes in book you find a vector written in bold italics. Matrix has usually capital letters and vector in bold italics. Here I have troubles to do it in bold italics, so I use this notation from physics, but it means vector. So how many? What are? This is a column vector dimension 2 times 1 because you have 2 rows and 1 column. W is again a column sorry, I told you row vector, column vector. This W is a column vector of dimension 2 times 1, 2 rows and 1 column. Okay. Now below I require to perform some operation. Compute, if it is possible, the following operation. So I go directly to the result, not directly, I mean A plus B. Since I have A plus B, I tell you what you have to do. Guys, I have the solution in the next page, but first look with me these matrices. A plus B is the sum between 2 matrices, but as I explained the theory, the sum or the difference, which is essentially the same, is feasible if and only if the matrices involved have the same dimension. But A is a 2 times 2 matrix, B is a 2 times 3 matrix, so the sum is not feasible. Guys, I explained everything in here, so you don't have to write because everything is written here. So 2 times 2 plus 2 times 3, not feasible. A and B have different dimensions. So let me see the next one. A plus 2C. Well, A is a 2 times 2 matrix. C is a 2 times 2 matrix. If you multiply a matrix like C by a scalar, as I told you, the scalar product between a matrix and a number is always feasible, and the result is a matrix with the same dimension whose elements are simply multiplied by 2. So 2 times C is still a 2 times 2 matrix. So A plus 2C is feasible. So first of all, compute 2 times C, and then add A. So now we are going below. Oh, C, not X. C times 2, sorry. 2. Here is 2. Okay, 2 here. So I copied A, so I copied everything essentially, you see. Then I copied again A, and I did the scalar product. 2 times 2, 2 times 1, 2 times 0, 2 times 2. And you get immediately 4, 2, 0, 4. So this is the operation that I've shown you before, K times a matrix. And this is very easy. Then you can make the sum. The sum is simply, you have simply to sum the corresponding element of the two matrices. So 1 plus 4, 5, 2 plus 2, 4, minus 1 plus 0, minus 1, 0, plus 4, 4. So you see how easy. Now I ask it to compute A plus A transpose. Is A plus A transpose feasible? Well, it depends. A is a 2 times 2. A transpose is obtained by exchanging the rows of A with its columns. So the columns of A are now the rows of A transpose, and the rows of A are the column of A transpose. So simply exchange this number with this one, and what you get? Again, a 2 times 2 matrix. So in this case, this operation is feasible because these two matrices have the same dimension. So first I copied A. Then here I computed the transpose. I told you have simply to exchange the rows of A with its column, which is the first row of A, guys. 1, 2. Well, 1, 2 is the first row, first row of A. So it's the first now column of A transpose. So see, I copied. This one is the second row of A, so it's the second column of A transpose. You see, this is simply transpose. I told you, by looking at the exercise, you see that the concept I described before are very, very easy to implement, so it's not difficult at all. Now again, sum, may perform the sum, 1 plus 1, 2, 2 plus minus 1, 1, minus 1 plus 2, 1, 0, plus 0, 0. Okay, guys. Now, the other operation are asked to compute is the following. A times A transpose. Is the product A times A transpose feasible? So right below the dimension of the two matrices. A is a 2 times 2 matrix. Its transpose is a 2 times 2. So what you have to look, the product is feasible, as I told you, if the columns of the first matrix and if the number of columns of the first matrix is equal to the number of rows of the second matrix. So you see that I checked first these two numbers. For this reason, I did this small segment below, this small line. So since these two numbers are equal, the product is feasible, and the result is a matrix. Look that I put this number and this one inside the circle, because the result is a matrix with a number of rows given by this number 2, and a number of columns given by this number, the column of A transpose. Now we are going to see how to perform the product. As I told you, you have to multiply. This product is called row column product, because you have first to consider the first row of A, and you have to multiply this first row by the first column, and you write here the result. Then you have to multiply the first row of A times the second column of A transpose, and you write it the result. After having exhausted all the operation involving the first row of A, go to the second row of A, so which is this one, and here you have to report the product between the second row of A and the first column of A transpose, and here you have to report the product between the second row of A and the second column of A transpose. So, but the product, what kind of product is this one, guys? The first one, look at the first one. 1 times 2, what is it? Sorry, this is a row vector. of dimension, how many rows? 1. How many columns? 2. So this is a vector of dimension 1 times 2. Multiply by this vector, the first column of A transpose, which is a vector 2 times 1. So this is exactly the inner product I explained before. Remember, to compute the inner product, you have to multiply the element occupying the corresponding position. So you have to multiply, which is the first element of this vector? This one. Which is the first element of this vector? This one. So you have V1 times W1. So you have 1 times 1. Plus remember, V2 times W2. So this times this. So you have 1 plus times 1 plus 2 times 2. I repeat. Now look at this product, the product between this vector and this one. You have 1 times minus 1 plus 2 times 0. And I wrote it here. Then you have, we exhausted all the operation involving the first row of A. Now go to the second row and repeat everything. First row times first column. Again, is the product. You can do the product because it's again a scalar or inner product. So minus 1 times 1 plus 0 times 2. And this is exactly what I wrote here. Then minus 1 times minus 1 plus 0 times 0. And this is exactly what I wrote here. Now do the operation, and what you get is this matrix, simply 1, okay, 1 plus 4, 5, okay, but now I think to make this product, I don't think to explain nothing. I need to do these operations. So now we repeat it again, okay, we need to learn the product, how to work with the product. Then I ask it to compute the product between A and B, if this product is feasible. The product AB is feasible right below the dimension of the matrices. A is a 2 times 2 matrix. B, we saw before, is a 2 times 3 matrix. So what you have to do? You have to look always first at these two numbers. Are these two numbers equal? Because if these two numbers are equal, then the product is feasible. Yes, they are equal. And the result, again, is a matrix with dimension. You have to look at this number and this one, 2 times 3. So now we are going to do this product. So I copied the matrix A and I copied the matrix B. Again, the product is called row column because first you have to exhaust all the multiplication between the first row of A with all the column of B. So first product is between this vector and this vector. Again, the result is 1 times 1 plus 2 times 2. You see, I wrote it here. Then the number you have to put here in the second column of this matrix is the product between this row and the second column of B. So 1 times minus 1 plus 2 times 1. And this is exactly what I wrote here. What do you have to write here? The product between the first row and the third column of B. So 1 times 0 plus 2 times 2. Go below. The row times the column again. Minus 1 times 1 plus 0 times 2. Then, which is the element you have to put here? Minus 1 times minus 1 plus 0 times 1. Exactly what I wrote here. What you have to put here? Minus 1 times 0 plus 0 times 2. Then, if you make this very elementary operation, you get this matrix. Which is the dimension of this matrix? It's a 2 times 3 matrix, exactly as predicted, not predicted, okay, exactly as we knew from the beginning, you see. Now go on with other operation. Now, B times A. B times A is a 2 times 3 matrix. A is a 2 times 2 matrix. You have to look at this number and at this one. Are these numbers equal? No. Therefore, the product is not feasible. So you see, this is an example that shows you that in general, A times B for matrices is not equal to B times A. In this particular case, A times B was feasible and the result was a matrix of dimension 2 times 3. In this case, B times A is not feasible. Why? Because 3, the number of column of B, is different with respect to 2, the number of rows of A. Now, is the product VW feasible? Well, which is the dimension of V? Is a 2 times 1 vector, a column vector. W is a column vector. So compare the number. What do you think? Is the product feasible? Are these two numbers equal? No. So this product is not feasible. Now I ask you, is the product V times W transpose feasible? Now we look. V is always 2 times 1. The transpose of W is simply obtained by exchanging the rows of V with its column. So is a, what is it? A 1 times 2. So this is a column vector, and this is instead now a row vector. You see 1 row and 2 columns. Is the product feasible? Yes. Why? Because this number and this number are equal. And the result is what? A matrix of dimension 2 times 2. So do the product with me. So I wrote here V. I reported V transpose with W transpose. W was a column vector with elements 1, 3. Its transpose is a row vector. Remember, you have to multiply the row, the first row of this matrix by all the column of this one. Which is the first column, the first row of V is 2. So 2 times 1, which is 2. Then 2 times 3, which is 6. Then go below. Second row times first column, 1 times 1. First row times second column, 1 times 3. Is the product V transpose times W feasible? Well, V transpose, V was 2 times 1. So V transpose is a row vector 1 times 2. W is a column vector 2 times 1. This number and this number are equal, so the product is feasible, and the result will be a matrix of dimension 1 times 1 is a scalar. This is exactly an example of V transpose times W is exactly what we defined previously as inner product or scalar product. In fact, we have 2, 1, okay, because I have to transpose it, times 1, 3. So you have 1 row times 1 column. So 2 times 1 plus 1 times 3. And you get 5. Now do the product between A and I2. Which is I2, guys? I denote A is a matrix of order 2, and I denoted I2 as the identity matrix of order 2. So I2, identity matrix of order 2, if you remember, is a matrix, square matrix of order 2, whose diagonal elements are all equal to 0, the one on the main diagonal, I mean, A11 and A22 are equal to 1, sorry, and all the outside of diagonal elements are equal to 0. So I repeat. Okay, no, maybe I wrote it here so you can understand. I told you this is identity matrix. I want to repeat. All the elements of the main diagonal are equal to 1, and all the elements outside the main diagonal are equal to 0. So this is example of the famous identity matrix. You see, square matrix, this is the main diagonal, A11, A22, 1, and the element outside the main diagonal are equal to 0. As I told you before, if you multiply this element, is the identity matrix is the neutral element with respect to the product. But we are going to see if this is true, because I told you that if you do this times I2, this should be equal to I2 times A, which should be equal to A. Now we are going to verify with this example if this is true. So I copied A, I wrote the identity matrix of order 2. Now do the product. First row times the first column. 1 times 1 is 1, plus 2 times 0 is 1. You see here I avoided this case to report all the steps. Now you have to do this row times this column. 1 times 0 is 0, plus 2 times 1 is 2. So 2 minus that. Now we exhausted all the operation involving the first row. Go to the second one and start again. Second row times first column. Minus 1 times 1 is minus 1, plus 0 times 0, 0, so minus 1. Now, last operation, this row times this column. Minus 1 times 0 is 0, plus 0 times 1 is 0, so 0. Oh, and as you see, A is this matrix is exactly equal to this one. Now do I2 times A. I2 is this one, and A, it's this one, okay? Obviously, the product is feasible again, you see, obviously, guys, because 2, 2, 2, 2. Do the product. If you do this row times this column, you get 1. This row times this column, you get 2. Then this row times this column, you get -1. This row times this column, you get 0. So you see, this is equal to this one, which is equal to A. Now, another example. Suppose you have these two matrices, guys, these two matrices. A is a square matrix of order 2, B is a square matrix of order 2. And I ask you to compute A, B, and B times A if these products are feasible. Is A times B feasible? Yes, because A is a 2 times 2 matrix, B is a 2 times 2 matrix, but then what? You see, this number and this number are equal. So the result is a matrix of dimension this number times this one. So is a square matrix of order 2. We verify. Now we do it. So this is the first one and the second one. Again, what you have to do, here again, I wrote all the steps. You have to do this row times this column. So 1 times 1 plus 2 times 1. And you see it here. Then you have to do 1 times 2 plus 2 times 1 here. Then go to the second row, 3 times 1 plus 2 times 1. Then you have to do 3 times 2 plus 2 times 1. If you make this simple operation, you get this matrix. So you see that, as predicted, is a 2 times 2 matrix. Is the product B times A feasible? Yes. And the result, look, why is feasible? Because B is a matrix of dimension 2 times 2. A is a matrix of dimension 2 times 2. These 2 and these 2 are equal. And the result is a matrix of order 2. Oh, maybe now the product in this specific case satisfies because guys, in a lot of cases, A times B could be feasible, but B times A not feasible. In other cases, A times B can be feasible, B times A feasible too, but you may have, for example, guys, let me write some. Oh, here I have to do. For example, guys, before I go on, suppose that A is a 3 times 2 matrix, and suppose that B is a 2 times 3. So, is the product A times B feasible? Yes, this number and this number are equal, so the result is a matrix, call it, I don't know, C, with dimension 3 times 3. Is the product B times A feasible? B times A. B is a 2 times 3. A is a 3 times 2. Oh, you see. The product in this case is, again, feasible. And the result is a matrix D of dimension 2 times 2. So obviously, you see, this is a case in which A times B and B times A is feasible. So, why is feasible? You see, why are both feasible? Because you see that the number of rows, this happens because the number of rows of A is equal to the number of columns of B, and the number of columns of A is equal to the number of rows of B. So you see 3, 2, 2, 3. So in this case, they are both feasible. But as you can understand immediately without doing computation, these products are not equal, because the first one leads to a matrix, square matrix of order 3. The second one leads to a matrix of order 2. What do you think? Which is a necessary condition in order to have that the product A times B is equal to the product B times A. Obviously, a necessary condition is that A and B are square matrices of the same order. In fact, suppose that, as in this case, look, this is a 2 times 2 matrix, this is a 2 times 2 matrix, so both AB is feasible, obviously, and BA, and the result is a matrix of dimension 2, order 2. I told you, this is a necessary condition. Is this condition sufficient? Well, try to look at the example. So this is B, and this is A. Do the product. This row times this column, and you write it here. This row times this column, and you write it here. This row times this column, write it here. This row times this column, write it here. So you see, we got a square matrix of order 2, but look at the elements. You see that the elements are different. So, but I wrote it, guys, in the theory even if I avoided before to tell you this necessary condition. So the necessary condition for having A times B equal to B times A is that A and B are both square matrices of the same order. However, this is only a necessary condition, because obviously only in this case it could happen then A times B is equal to B times A is necessary, but it's not sufficient, as you can see, and this example showed, because you see they are not equal. They have the same dimension, but not equal. They are not equal. Another example, I asked you, are these two vectors, which is the dimension of this vector, guys? This is 3 times 1 vector, column vector, and this is the same, 3 times 1. Are these two vectors orthogonal? Remember, I told you that two vectors are orthogonal. This means perpendicular, but okay, we don't talk about geometry, guys. Are orthogonal if their inner product or scalar product is equal to 0. So, by definition, how can you compute the inner product or scalar product? You have to transpose V and multiply by W, because V transpose is a 1 times 3. Is a 3 times 1, so the product is feasible, and the result is the number. Alternatively, looking at the property of the inner product I've shown you before, you can even do W transpose times V. And this essentially simply means that you have to sum the product between elements in the same position. So, even if you do not transpose to transpose, yes, but you can do mentally, because you know that you have to multiply essentially elements V1 times V1 times W1, V2 times W2, V3 times W3, and you have to sum them. So you have 1 times 0, okay, plus 0 times 2 plus 1 times 0. Okay, but remember, I avoided to write V transpose because I know from definition that you have this product. But remember that V times V transpose is not feasible. Sorry, V times W is not feasible. V transpose times W is feasible because you must have always the same dimension. Okay, I avoided to write it, but if you want, I write it if you have problems. I write V transpose, which is 1, 0, 1, and so you have to do, as I told you, 1 times 0, remember, first row times this column, essentially, 1 times 0 plus 0 times 2 plus 1 times 0, exactly what I wrote here, which is 0. So, since the inner product between these two vectors is 0, these vectors are called orthogonal. Okay, you see that these operations at the end of the story were very easy. So it is not important that you are good in mathematics to understand these things. You see, the exercises are very easy. Obviously, if it is the first time, you have to look it again. But I know that this is very elementary, not difficult at all. Here, guys, I provided the definition of another important concept, the determinant. Now, the determinant of a square matrix, well, is I don't want to simplify. Of a square matrix is a function. No, I don't want to. Okay, I read it, but I don't want to create confusion.
is a function defined on the space of the square matrices of order n. So what does it mean? The determinant is a function whose argument, the so-called x. Remember, when you study a function, you have y equal to f of x, okay, y equal to f of x, and for every x in the domain, y assumes a particular value. This is a scalar function because it assigns a unique value, a one value for every value of x. So the determinant essentially is a function that assigns to each square matrix, okay, to each possible square matrix, a number. In particular, in fact, this means determinant means the domain is the set is represented by all the set containing the real matrices. Mn times n is the space containing all the real matrices with n times n element, that is square matrices, and it assumes values in R. But simply, guys, without avoiding to say these things, simply, given a matrix, I'm going to explain, given a matrix with number, how can you compute the so-called determinant? So, first of all, the things important you have to remember is the following. You can compute the determinant only for square matrices. That is, for matrices whose number of rows is equal to the number of columns. Okay? In particular, guys, the definition of determinant is given by recurrence, and I explain, but then I'll show with the example, so don't be scared. So let K be a scalar. A scalar means a constant, a number, okay, not a matrix, a number. Then the determinant of K, this is the definition, is equal to K. So the determinant of a number is the number itself. Okay. Suppose that you are able to compute the determinant of every matrices, square matrix of order n-1. So you know the determinant of all the square matrices of order n-1. Now I show you how to compute by definition following the definition, I mean the determinant of a matrix of order n. So this, I repeat, is the definition. The determinant of a matrix A of order n is given by -1 to the power 1 plus 1 times A11. A11 is the element on the first row and the first column of A. And you have to pre-multiply it by -1 raised to what? To the sum of these indexes, 1, 1. Times what? The determinant of the matrix A11. I wrote everything before, so don't have to write. Where capital A11 is the matrix which is obtained by deleting the first row and the first column of A. First row and first column. So if you delete the first row and the first column of A, you get a matrix, square matrix of order n-1. But there are no problems, because according to the definition, you know how to compute the determinant of all the matrices of order n-1. Then go on, plus, look again at the first row of the matrix A and the second element, which is the element A1, 2. First row, second column. Pre-multiply it by -1 raised to the power the sum of the indexes, 1 and 2. Times what? Determinant of capital A12. Capital A12 is the matrix you get by deleting the first row and the second column of A. So what you get? You get another square matrices of order n-1. But assume that you are able to compute the determinant of a matrix of order n-1, then this matrix, this determinant is known. Then you have to go so on and so forth along the first row of the matrix. Then, which is the last element of the first row? Is the element A1, how many columns? N. So A1n, and A1n must be multiplied by what? -1 raised to the power the sum of these indexes times the determinant of the matrix A1n. Again, these parentheses have been cut during the scanning procedure. So there is a parenthesis here. Determinant of A1n, which is this determinant? Is the determinant of the matrix you get by deleting the first row and the column number n. So it's a matrix of order n-1. And I wrote everything below. If you read, I wrote everything here. So this is the definition of determinant. The determinant, guys, then we'll see how to compute it, okay? Typically, the determinant is denoted as, in two alternative way, as that A, which means determinant of A, or this symbol are equal to the one of the absolute value, but the meaning is different, means determinant. We have these two vertical line and this sign inside the matrix A. Observation, I told you before, determinant can be computed only for square matrices. I show, for example, a very special case, which is useful, is the determinant of a matrix 2 times 2. And now, this is the first, I need to write, because I want to show the steps. I want to show the step. Special case, suppose you want, which is the determinant of a scalar, guys? The scalar itself. Another small matrix, which is the matrix of order, square matrix of order 2. Because you have square matrix of order 1, which is the scalar, square matrix of order 2, square matrix of order 3, etc., etc. So, obviously, the simplest one is the determinant of a scalar, which is the scalar itself. Then, the other simple case, less simple, but still simple, is the determinant of a matrix of order 2. Now, we want to apply the definition. Determinant of a matrix A. I denoted this element of A as A11, A12, A21, A22. We want to compute the determinant of this matrix. Guys, I provide here the steps, okay, because here are reported directly the final rule that you have to remember, because it simplifies a lot your life. You have to do, remember, apply the definition with me. Develop the determinant along the first row. Remember, you have to do -1 to the power, and simply follow what I wrote above. -1 to the power, the sum of this index, 1 plus 1, which is 2. Times what? Times the determinant of the matrix. Oh, sto andando troppo in fretta. Let me cancel. It's better I suggest the order. I follow the order. Let me. Oh, cosa devo fare? E qui non so dove devo cliccare già qui. Dove cacchio è la gomma? Ah, questa è la gomma. I want to follow exactly the definition, sorry. So, I told you, times what? This element, A11, A11, times what? The determinant, we follow exactly what I wrote, determinant of the matrix, you get by deleting the first row and the first column of A, and I call it capital A11. I'm simply following, guys, the definition above, okay? Simply following it. Plus, you have to go to what? Move along the first row. Now go to this element, which is element 1, 2. So plus -1 raised to the power 1 plus 2, which is 3, times what? The element A12 times what? The determinant of the matrix you get by deleting what? The first row and the second column. First row and second column. So determinant of A12, capital A12. Okay, now you can, if you copied it with me, you can add it here. And then equal. Okay, then this is equal to the next one. Now, look with me. So here you have -1 to the power 2, which is 1. 1 times A11. So I already write 1 times A11 times what? The determinant of capital A11. Which is the capital A11? Is the matrix you get by deleting the first row of capital A, so cancel this row in your mind, and the first column, so cancel this, and so what you get? The determinant of A22. But which is the determinant of A22? A22 is a scalar. By definition, determinant of K is K. So the determinant of A22 is A22. And then you have plus what? -1 to the power 3 is minus, so I already write minus what? The element A12, I copied it, times the determinant of A12. A12 means delete the first row of A and the second column of A. So this times this. So this determinant of A12 is simply the determinant of H1. But H1 is a scalar. The determinant of the scalar is the scalar itself. So you got this very useful formula that allows you to compute quickly the determinant of a matrix of order 2. And it's very easy to remember. Why? Because to compute this determinant, look, what you have to do. The product of what? A11, A22. But A11, A22 are the element of the main diagonal. So A11 times A22 minus what? The element of the opposite diagonal minus the product of the element of the opposite diagonal. So this times this minus this times this. And this is a very important rule because it simplifies, as we will see in the exercise after the break. But still, I need to tell you something else. Theorem. Let A be a square matrix of order n times n. Essentially, guys, don't read here. Read what I directly the explanation I provided below. This theorem establishes, guys, that you can compute the determinant of a matrix by developing it not necessarily along the first row as we did in the definition, okay, and as we did in applying the definition of determinant here, but you can develop it along the line you prefer. You can develop it by following the second row if you prefer it. You can develop it by compute the determinant by developing it along the third row. Okay, but the theorem established something more. It's established that you can even develop the determinant along the column you prefer, and the result will not change. So guys, I provided the definition of the determinant by recurrence by developing it along the first row of the matrix. But you can develop the determinant along the row or along the column you prefer. Why? Well, as we will see, depending on the specific exercise you have, sometimes it's convenient to compute the determinant along a particular row or according to a particular column, okay, because this will not change the final result, but will simplify the number of computation you have to make. And let me see. And this is what I told you. This is essentially what I told you. And last, let me finish these things and then we do the break. The scalar capital Mij, which is defined as minus 1 times I plus j, determinant of ij, is called cofactor of the element ij. Cofactor of the element ij. We don't need it now, but later. And determinant of the matrix obtained by dilating the ith row and the jth column is called minor of ij. This is called minor, and this is the cofactor. Going back for a moment. So here the determinant is computed here by considering what? A linear, we say, combination of the cofactor, for example, of the first row with coefficient A11, A12, A1n. But okay, I don't want to complicate your life with these things. Okay, guys, I think it's better to have now 15 minutes of break. Okay, well, come back at 11:45, okay? 11:45, we continue. We will see the property of determinant, something else, and we'll see then exercises and some property. Okay, now 15 minutes of break, guys. Okay.
Okay, thank you.
Thank you, welcome, thank you. Va o non va? So guys, in a moment we start again. Let me, no, my desktop. Okay, guys. So now we continue. We're going to look at some properties of the determinant. Okay, some properties of the determinant. And so let me take. Okay, I told you already that you can develop determinant along the row or the column you prefer. Then I'm simply, suppose you have now two matrices, A and B, are both, yes?
We can
you
see,
guys?
No.
You can't see. Porca miseria, team. Now, let me try again. Perché team fa così? Why? Are you able to see now, guys?
No.
Ma porca miseria. No, dico con voi, grazie. Thank you, guys. I'm saying porca miseria to team. Oh, team. So let me go out. Let me share again. We try. Can you see now?
Yes.
Oh, no. Thank you. Thank you. So, properties of the determinants. Okay, the determinant of a square matrix, remember, because you can compute the determinant only for square matrices. So, determinant of A is equal to the determinant of the transpose. If A has a row of zeros, then the determinant of A is 0. If alternatively A has a column of zeros element, so a column containing all zeros, then the determinant of A is equal to 0. Only the intuition, guys, about the first property and the second one. I told you that you can develop the determinant along the row or the column you prefer. So, and the result does not change. For example, suppose I develop the determinant of the matrix A along the first row. The first row of matrix A is also the first column of matrix A transpose. Okay, so if I develop the determinant of A along the first row or along its first column, then the determinant is unchanged, but I repeat. So I repeat again, sorry. Determinant, if you develop the determinant along the first row of A or along the first column of A, the result does not change. Okay, so suppose I develop the determinant of A along the first row. And I develop also the determinant of A transpose along the first row of A transpose. But the first row of A transpose is the first column of A. And so, obviously, the determinants are equal. Why the second property? The proof of the second property is very intuitive. Suppose you develop the determinant of A along the row containing all the zeros. If you look at the definition of the determinant, you have a sum of zeros, because all the components the element of the sum of in the determinant are multiplied by a11, but a11 is 0, plus minus 1 to the power 1 plus 2 times a12, but a12 is equal to 0, etc., etc. So I'm saying that all the elements a11, a12, a13, a14 are equal to 0. If you develop it, assuming, for example, that the 0 is the first row. So if A has H, and as I told you, we will see everything with example also. If A has 2 equal rows or 2 equal columns, then the determinant of A is equal to 0. Okay. So if you have that 2 columns or 2 rows are equal, then the determinant of A is equal to 0. If A has 1 row or 1 column multiple of another row, for example, suppose that the third row can be obtained by multiplying by 2 the first one. Okay, so all the elements of the third row are obtained by multiplying the ones of the first one by 2. Then you have that the third row is a multiple of the first one, and so the determinant is 0. Okay, this is true. Obviously, you have to compare row with row and column with column. Alternatively, if a column is a multiple of another one, then the determinant is equal to 0. If A has 1 row or 1 column that can be expressed as a linear combination of other rows, this row, or other column, this column, then the determinant is equal to 0. Linear combination means, for example, guys, suppose that the third row, guys, is equal by the first row plus the second. So in this case, we have that the third row is a linear combination of the first 2 with coefficient 1 and 1. Let me repeat another example. Suppose that you have that the row number 4 of a matrix can be obtained by first multiply the first row by 2, then add the second multiplied by 3. Suppose that 2 times the first one plus 3 times the second row is exactly equal to the fourth row. We say that the fourth row is a linear combination of the first 2 rows of the matrix with coefficient 2 and 3. Suppose, for example, that the second column of a matrix can be obtained as the first column plus the third minus the number 4. So the column number 4. So in this case, you have that the second column is a linear combination of all the other columns of the matrix, in particular with coefficient. Remember, the first row plus the third with coefficient 1 associated to the first, 1 associated to the third, and I told you minus the fourth. So, and with minus 1 as a coefficient associated to the fourth column. So, in all these cases, guys, I don't want to talk too much, but I simply want to tell you that the property I just told you is the general case, including the previous one, because saying that one row is multiple of another, it means that, what does it mean? For example, suppose that the fourth column is 3 times the first one. This means that the fourth column can be expressed as a linear combination of the other with coefficient 3 associated to the one first, 0 to the second, and 0 to the third. Saying that A has 2 equal row or 2 equal column, again, is another special case of a linear combination. Suppose you have a matrix 3 times 3, and suppose that the third column is equal to the first one, So this means that can be obtained by multiplying the first one plus 0 times the second one. So again, is a linear combination of the other 2 with coefficient 1 and 0. Yes, also the first one, but I don't want to tell. Also, this one is a special case, but we should have explained other things, so I want to avoid it because I think that you are already confused enough. If an element of a row or of a column of a matrix A are multiplied by a constant, then also the determinant of A is multiplied by that constant. So suppose you have determinant of k to the power A in general, then the determinant of this new matrix is determinant of A to the times k to the power n. Why? Because if you multiply only the element of a row, suppose you multiply only, sorry, I repeat better. Suppose you multiply only the first row of A by the constant k, then the result is k times determinant of A. Suppose you multiply two rows of A by k, then the determinant of this new matrix is determinant of A to the power times k to the power 2. So if you multiply instead all the elements of A, that is all the rows of A, by k, how many rows A? We are talking about a matrix, a square matrix of order n. So it has n rows. So therefore, of a matrix multiplied by a constant is given by the determinant of that matrix times k raised to the number, the rows of that matrix. Okay. So if you multiply a 4 times 4 matrix by a constant k, the determinant of k times A is the determinant of A times k to the power 4. Another property, if you exchange the position of two rows, one row with another row, then you have to change also the sign of the determinant. If you exchange the position of two columns, one with the other, then you have to change the sign of the determinant. For every change you perform, you have to change the sign of the determinant. So if you exchange the first with the second, you have a change. Suppose that you also exchange then the new second with the third, you have another change of sign, so minus, minus, plus. So for every change, additional change, you have to change again the sign of the determinant. Now I think there is a few last property, and then which are the following. Determinant of AB, suppose that AB are both square matrices, but I wrote it above, okay? A and B are both square matrices, obviously of the same order. Then there is an important theorem called Binet theorem that establishes that the determinant of AB can be also computed as a product of the determinant of each of these matrices. And this property sometimes can be very useful to reduce the number of computation you have to do, as you will see in the example. Suppose that capital AI is a matrix of order n, and suppose you have n matrices of order n. What have you ever seen this? I don't remember if you. Oh no, I wish you show the. I think it's the first time you see this symbol with me. This is a capital pi, as there exists the sign of the sum from I equal to 1 to n, which is a capital sigma. There exists also this huge capital pi. That means product. What does this mean, guys? This means determinant of parentheses capital A1, which is the first matrix, times capital A2 times capital A3 times etc. capital AN. So it's a way to simplify the product, to write in compact form the product of n elements. So suppose you have to compute the determinant of a product of 100 matrices. So in this case, you can compute first the product of each, I mean, A1 times A2, the first, then the product by A3, then the product by A4. So it's quite very, very long. And at the end, compute the determinant of the resulting coming out from the product. Alternatively, by using Binet theorem, you have the determinant of a product is the product of the determinants. So you can write product of the determinant. So instead of in this way, guys, you don't have, if you use the first side I told you, first you have to multiply all the matrices involved. So it's a very, very long computation. And then compute the determinant of the matrix resulting from the product. But according to Binet theorem, what you can do alternatively, you can simply compute first the determinant of each of these 100 matrices, and then multiply all the determinants. So this is called, I told you, Binet theorem, where AI are, repeat, matrices, square matrices of order n, because remember, you can compute the determinant only for square matrices. It follows from Binet theorem, suppose you have to compute the determinant of A to the power 3. A to the power 3 is A times A times A. So determinant of A to the power 3 is like the determinant of a product. So using Binet's theorem, you would have determinant of A times determinant of A times determinant of A, so that you can write directly determinant of A to the power P. So this is also a very important property, because if you have determinant of A to the power 10, to compute A times A times A times A times A times A times A is long. You can write directly determinant of A and raise the result to the power 10, where P, I repeat, is an integer number, natural number. Determinant of IE to the power n is simply 1. Oh, aiuto, mi sono spaventato. Guys, I tell you already a property here. Can you add a property? I wrote it later, but it's another important property. This property establishes that the determinant, let me go on. Let me go on. So maybe you don't have to write. Let me go on. Skip for the moment this part. Skip for the moment the exercise. We will do them in a moment. In a moment. The last 5 minutes. I go here because I want to tell you something else and the property. Okay. I want to tell you something else. Guys, ecco, we are here. No, so you don't need to write. Special square matrices. Special square matrices are the following, guys. The diagonal matrix. Diagonal matrix, guys, is a matrix such that all the elements outside the main diagonal are null. So one example we have already seen is the identity matrix, because the identity matrix is a matrix such that all the diagonal elements are equal to 1, but all the elements outside of the main diagonal are equal to 0. Then another special case are the triangular matrices, are still, I repeat, square matrices, and we have two types of triangular matrices: lower triangular matrices and upper triangular matrices. A lower triangular matrix has only 0 elements above the main diagonal. That is, what I want to say is that all the elements above the main diagonal are necessarily all equal to 0. In an upper triangular matrix, all the elements below the main diagonal are 0. This does not I mean, you can have also other 0 above the main diagonal, but the important thing is that all the elements below the main diagonal are 0. And an important thing is that if you have, suppose that L is a lower triangular matrix, then the transpose of L, exchange the row with the column, is an upper triangular matrix. Why I'm explaining this now? Because here I provided I told you another important property that can be obtained immediately by simply doing the general computation of the determinant I explained. That the property is the following. You don't have to write because I wrote it here. The determinant of a diagonal matrix, the determinant of a triangular matrix, can be computed very easily without having to perform all the steps I explained, because it is simply the product of the diagonal elements. So it is simply the product of a diagonal elements. So therefore, we say that a triangular, so guys, intuition, a triangular or a diagonal matrix has a 0 determinant if at least one of the diagonal element is equal to 0, since the determinant is the product of the diagonal elements. Since I'm here, I tell it without proof. I'm simply saying here, guys, that a symmetric matrix is a matrix such that is a square matrix, guys. We are talking about special square matrices, such that its transpose is equal to A. No, you don't need the. And an orthogonal matrix, on the contrary, guys, is a matrix such that A times A transpose is equal to A transpose times A, which is equal to the identity matrix. And as I will explain in a moment, no, I'll tell it later. because I think it's better to do exercises now. Now let me tell only the last thing, guys, and then we do the exercises. The last things is the following. Trace that for the moment, guys, I explained you two operations, the determinant and no, only one operation, the determinant. I explained several properties of the determinant. Okay, several properties. There are other two important operations between matrices, which are the computation of the inverse and the trace. And yes, really 10 minutes and then no, 6 minutes I want to finish, and then we do exercise to see everything so you can relax yourself. Because I understand that with all this property now you have your confusion in your mind and your mind is exploding, so don't be scared. I know, so don't be scared. The trace, guys, is defined is simply the sum of the diagonal element of the matrix. So it's simply the sum of the diagonal element of a matrix. Here I reported the properties, guys, but that are very, very, very straightforward. The trace of a constant is the constant itself. The trace of a constant that multiplies a matrix can be computed also by computing first the trace of the matrix and then multiplying the result by k. But this is obvious. Why? Because the trace is the sum of the diagonal elements, okay, of a matrix. If you multiply a matrix by a constant, the diagonal elements of this new matrix are equal to the diagonal elements of A, each one multiplied by the constant. So collect the constant and you get k trace of A. Obviously, the trace of the sum is equal to the sum of the traces. The trace of a difference is the difference of the traces. Again, obviously, because the trace of AB is the sum of the diagonal elements of the matrix A plus B. But the elements of the diagonal, for example, which is the element of this matrix in the position II, is AII plus BII. So sum of the traces, or if you have the minus, difference of the traces. If trace, if AB is feasible and also B times A feasible, and suppose this product raises a square matrix, otherwise it does not make sense to compute the trace, and B times A raises to a square matrix. So I repeat, suppose A and B are square matrices. Suppose also that both AB and BA are feasible, and this occurs if both matrices are matrices of order are square matrices. Then what happens? You can compute the trace in these ways. The trace of AB is equal to the trace of BA. So you can either do A times B and then compute the trace, or B times A. So even if the final matrices are different, suppose AB is a 3 times 3 and BA is a 2 times 2, they have the same trace. So again, suppose again this product is feasible, and what you get is a matrix of order n. We will still have to see what it is. This is called inverse, and I will say you. If you have the inverse times of B times A times B, suppose that again this is a square matrix. Well, it is possible to show that in this case the trace of this matrix is simply equal to the trace of A. B not singular means that you can compute the inverse, but okay, I still have to explain it. So here are some properties. You don't have to remember, guys, necessarily of this property, okay? These are basic, elementary, but these are more important for econometrics than for mathematics, this property, because very often you work with the trace in econometrics. I mean, you work also in mathematics with the trace, but you don't need in mathematics, typically, I mean, in what you are going to do with Professor Dieci, you don't need this formula, but in econometrics, well, in some cases you need it. So the trace, simply, what is important to remember mainly? That the trace is the sum of the diagonal element. Remember the definition of determinant, the property of the determinant, and let me tell you only the last concept, and then with the theory we really finished. The inverse, I told you, determinant and trace can be computed only for square matrices. Also, the inverse can be computed only for square matrices. In particular, let A be a square matrix, a necessary and sufficient condition for the existence of the matrix A to the minus 1, which is still a matrix of order n, called inverse matrix of A, that is, for the existence of a matrix A times minus 1 such that A times A minus 1 is equal to A minus 1 times A, equal to the identity matrix, is that the determinant of A is different from 0. So I want to remember that A is a square matrix, and the inverse operation is defined only for square matrices. However, the inverse of a square matrix is still a square matrix, and this square matrix with the same order of A exists if and only if the determinant of A is different from 0. So if determinant of a given matrix, square matrix, is equal to 0, then the inverse does not exist. If it exists, this is the inverse, guys, is a matrix such that if you multiply A by its inverse, or if you pre-multiply A by the inverse, I mean, this is equal to this one, and what you get is the identity matrix. Essentially, guys, for numbers, suppose you have a number, guys. Which is the reciprocal of this number, guys? Is 1 over A, okay? Which is the product between a number and its reciprocal. Obviously, you have also that is equal to 1 over A times A. If you do the product, you get 1. But, guys, the reciprocal of a number exists if A, the number, is different from 0. Okay, so what 1 over A plays, what the reciprocal of a number is for numbers, A minus 1 is the reciprocal of a matrix. So what I want to say that this is the concept of a reciprocal of a number, and the corresponding concept of this, guys, is the concept of reciprocal of a number. The corresponding concept for a matrix is represented by A minus 1. You see, these are the properties. They are the same. I mean, the corresponding property. However, a reciprocal exists if and only if A is different from 0. Remember that 1 over A can also be written, if you like it more, as e to the minus 1. So it's more similar written in this way. But the inverse, the reciprocal exists if and only if the A is different from 0. The inverse of a matrix, or the reciprocal of a matrix, exists if and only if the determinant is different from 0. Okay, let me see. Yes, the inverse of the inverse is A. If you have a product and you have to take the inverse, you can do B to the minus 1 times A to the minus 1. So you have to change the order between B and A. Well, obviously, A and B is a square matrix. B and A are square matrices of the same order. If you have to consider the transpose of the inverse, alternatively, you can consider the inverse of the transpose. And the last important things I want to tell you is that the determinant of the inverse is equal to the determinant of A raised to the minus 1, which is the determinant of the inverse is the reciprocal of the determinant of A. Now, I think, no, avoid this, guys, avoid. Unless you want, because you don't need it for mathematics, you don't need to compute the inverse directly from for mathematics. Now, guys, please, now sorry, I know you are tired, you are dying, now we do some exercises, okay, to play together with all these concepts that I know that are too many to see them all in a day. I mean, without studying, okay, also, but we will review everything. So I asked here, no, we do not compute A minus 1, no, because I didn't explain how to compute it. We compute the determinant of A, and simply we answer, does the inverse exist? Remember, now we're going to compute a determinant of A. If the determinant of A is different from 0, then the inverse exists. So we compute first determinant of A, then determinant of B, and let me go to the solution. I hope I copied. Oh, I explain so with the matrix under our eyes, otherwise you do not understand. So here, guys, let me see, I develop the determinant along, no, let me see, because obviously, wait, I need to understand, no, since I explained what I did below, I need to understand which row I selected. I think I selected the first one. No, I selected the second one. Yes. Guys, as I told you at the beginning, no, because I want to follow what I did, otherwise I create confusion. As I told you, I explain why. Because as I told you, you can compute the determinant along the line, the row, this one, this one, or along the column, this one, this one, you prefer. Guys, remember that I told you, in the definition, I developed the determinant along the first row, but then I gave you a theorem that established that you can compute the determinant by developing it along the row on the column you prefer. Why you prefer? Well, guys, it is always convenient to develop the determinant by computing it either along the line or along the column containing the biggest number of zeros. For example, the most convenient in this case is the development along either the first or the second row. The second or the third row, or the first column or the second column, because you have a zero. Why is important? Now, for example, develop it along this row. Remember, apply the definition. This element is in the position second row, 1 column. So the indexes are 2 and 1. So you have to do, guys, I'm saying, but then we go below to show, you have -1 to the power. Pay attention, then I wrote everything below. -1 to the power 2 plus 1 times what? 1, which is the element A21, times the determinant of the matrix you obtain by cancelling A21, cancelling this second row, A21, this one. So the determinant of 1, 1, 1, 1. Go below and you see immediately, yes, that is exactly what I told you. Then go to the second element of the row, which is the element 0. So now go to this element. This element is in the position 2, 2. So you have plus -1 to the power 2 plus 2 times the element itself 0 times, which is the position 2, 2, times the determinant of the matrix you get by deleting the second row and the second column, which is 1, 0, 0, 1. Now go to the last element of the row. This one. This element in the position 2, 3. So you have plus -1 always to the power, which is the position 2 plus 3. Times what? The number you have here, 1, times the determinant of the matrix you get by deleting the which is the column, is the third column, and which is the row, 2. So delete the second row and the third column. So you have 1, 0, 0, 1. Okay, now do with me the computation. -1 to the power 3 is -1, times 1 is 1, which is the determinant of this matrix, guys. This is a matrix of order 2, and remember, we find out that you can compute easily the determinant of matrix of order 2 simply by doing the product of the element of the main diagonal, 1 times 1, minus the element of the opposite diagonal, 1 times 1, which is 1. Now, guys, here I won't compute nothing. Why? Because you have a 0, so it's not necessary to perform computation, because you have, this is a number times 0. This is a number, so it's 0. So you don't even have to look this one. So I did it because it was the first time. But whenever you have a 0, you don't have to do the corresponding computation. For this reason, it is always convenient to develop the determinant along the line or along the row row or the column containing more zeros, because you have less terms to sum. Here, guys, I wrote it, but only for a reason, only to explain it. But you could have avoided it immediately. Okay, and then which is the last term? -1 to the power 5, which is -1 times what? The determinant of this matrix, you have to do again 1 times 1 minus 0 times 1, which is minus 0. So do computation, you get minus 1. So since the determinant of A is different from 0, you can compute, if you want, the inverse. But I told you I will not explain how to compute the inverse, so we can skip it. Here only if one is interested, but because you don't have to compute explicitly the inverse, you must know what the inverse is, but you don't need to compute with an inverse with your hands in a mathematical method and tools. Now, I asked then to compute, che pagina è? Troppo... sono perso, dove sono gli esercizi? Here. I asked you to compute the determinant of this matrix. Guys, before going below, I want you to observe something. Questo cancella. Cancella malissimo.
Any problems today? The worst lecture of all of ever. Let me share my desktop again. Dove sono? Guys, do you see the worst lecture ever, guys? Now, guys, are you able to see my desktop?
Yes, we do.
Okay.
We see the
So
PDF.
guys, if you have still a problem today, I like you to go earlier because half an hour, we are still half an hour, and you know that typically I give you the last 15 minutes. If you have another problem, we stop because guys, I know you only are simple exercises. So what I was saying, if you go below, the matrix V is obtained by multiplying the second and the third row of A, please write A, by 2, of A by 2, page 10, of A by 2, so determinant of B is equal to 2 to the power 2 times the determinant of A. Determinant of A has been computed in point A and was -1, so 2 to the power 2 is 4 times -1 is -4. Let me go above because I do not have that. Consider this matrix. Again, one can be always compute the determinant by developing it along the row or the column you prefer more. However, since here I wanted to show some property, I want you to make a comparison between matrix A and matrix C. You see that I exchanged the first column of A with the third column. You see, now the third column is here and the first one is here. So remember that I told you in a previous property that if you exchange two columns or if you exchange two rows, then the determinant change of sign. Since we simply changed the position of this row with this column, with this column to get this matrix, the determinant of C is simply equal to minus the determinant of A. The determinant of A was -1, so even without doing computation, we know that the determinant of C is 1. I do not go below because I simply explained it, so you have point C I wrote, okay? The explanation I just provided you. Look at matrix D. And again, you can either develop the determinant applying the definition along the row or the column you prefer. However, since I know that here I made some tricks to apply properties, compare matrix A and matrix D. Well, I observe something first. Okay, guys, you're not required to find out these differences in general. Okay, you make the computation, but here only to play with the property. Imagine to exchange the first row of A with its second row. So here you have 1, 0, 1, here 1, 1, 1, here 0, 1, 1. Okay, you have a matrix in this way. So, but then observe, multiply then the matrix obtained by exchanging this row with this row in this way. Multiply the new first row by 2, the second new row by 3, and the third row by 1/2. So I repeat, are you able to see that here, first I changed it, I got the matrix D by exchanging the first row of A with the second one. And then I multiplied the first row by 2, the second row by 3, and the third by 1/2. So in other terms, to get D, first I exchanged two rows. Which is the effect on the determinant? The exchange of two rows, one with the other, to exchange the sign. So remember, we exchange the sign. Then if you multiply a row of a matrix by a constant, also the determinant of that matrix must be multiplied by that constant. But observe, I multiply by 2 the first one, by 3 the second one, by 1/2 the third one. So what you have to do, the determinant of D is equal to minus
because we exchange this row with this one. What? Determinant of A times what? 2 times 3 times 1 over 2. Okay, I remember that I forgot. So remember, please, guys, put a minus here. Yes, I remember that I already modified it last year, but I forgot to write it. Remember, D minus, because I told you there is the change of the order, then you have times 2, times 3, times 1 over 2, determinant of A. This is due to the fact that we exchange the first and the third one. So put plus here. So plus 3 is the determinant of D. If you do not believe me, at home, do the computation of the determinant by doing all the steps, because the computation are short. Okay. Now go again above. So the determinant is 3. Now we need to compute the determinant of the matrix E. You can compute the determinant of the matrix E again by applying the general definition if you want, and developing it along the row of the column you prefer. But since here I want to make some trick, look, compare it with, for example, matrix A. Yes, the first row is equal, the second row is equal, and look at the last one. Well, it's not, yeah, the information is not directly from matrix. Look here, look at the third column, the third row, sorry. The third row, look, 1 plus 1 is equal to 2. 1 plus 0 is equal to 1. 1 plus 1 is equal to 2. So, in this case, we have that the last row of the matrix A is a linear combination of the first two, with coefficient 1 and 1. In other terms, it's simply the 1 times the first row plus 1 times the second row, and this gives you the second one. Simply, the last row is the sum of the first two, so it's a linear combination. And I told you, when a row of a matrix is a linear combination of the other rows, or when a column of a matrix is a linear combination of the other columns of the same matrix, then the determinant is equal to 0. So here, without having to do computation, you know that the determinant is equal to 0. So can you compute in theory the inverse of e to the minus 1? No, you cannot compute it. Why? Because the determinant is equal to 0. It was only an additional question. Now, go to F. I told you that when you have a row or a column of 0, the determinant is equal to 0. As I told you, so determinant of F obviously is 0. If you do not believe me, develop the determinant along the second line. So without doing computation, you get 0 immediately. Otherwise, develop it along the line or the column or the row you prefer. Now, which is the trick I applied here? Bo, I really do not know. For example, look at this matrix, which is what is convenient for you guys. Or maybe here there are no trick at all. However, guys, in this moment, I'm not able to see if I did some particular operation. I need to check it, but okay, I don't want to lose time by looking, but I don't think I think that here the purpose of this exercise was simply to show you that it is convenient in this case to develop the determinant. Okay, you can develop it along the line you prefer, but it is convenient, I think, it's convenient to develop it along the first column because you have 2 zeros. So probably what I think is that here you have no tricks, but I did only to let you to select at the first column the one to use to develop the determinant. In particular, you see you have, look at the first column. So develop it along the first column with me. So which is the element of the first column? 1. 1, which are the index of 1? 1 and 1, okay, because the element in the position 1, 1. So you have minus 1 to the power 1 plus 1 times what? The element itself times what? The determinant of the matrix you get by dilating position A1, 1. So by dilating the first row and the first column. So determinant of 2, 2, 4, I think 1. Let me see below, which is the page. Yes, this was the trick, guys. We develop the determinant along the first column. So this is 1, 2 times 1 is 2, minus 4 times 2, minus 8, so minus 6. Now let me see, let me go above. Determinant of this one. Guys, this is an example of a diagonal matrix. Why? Because all the elements above the main diagonal is this one, okay? A11, A22, A33. All the elements above the main diagonal and all the elements below the main diagonal are 0. And as I told you before, the determinant of a diagonal matrix is can be simply computed by doing the product of the diagonal elements. So 1 times 2 is 2, times minus 1 is minus 2. Obviously, you can develop the determinant alternatively along the row of the column you prefer. And what you have here, I hat, which is the determinant of I hat, capital I hat. Well, which kind of matrix is this one? I told you this is a square matrix, and in particular, obviously, otherwise you cannot compute the determinant. You see, all the elements above the main diagonal are equal to 0. So this is a lower triangular matrix because all the elements above the main diagonal are 0. And I told you, for diagonal matrices or for triangular matrices, you can compute very quickly the determinant simply by doing the product of the diagonal element. 3 times 4 is 12, times 2 is 24. Okay, so the determinant is 24. So let me go below. Okay, here guys, I explained everything, okay, so the things I told you. Now, determinant of a square. There is a stupid way to solve this exercise and a smart way. The stupid way is the following. Take the matrix A, do the product with the matrix A, so you have to do the product between matrices, and then compute the determinant of a square. Alternatively, use Binet's theorem, because I told you the determinant of a to the power p, where p is an integer number, is equal to the determinant of a raised to that number. So here, the most convenient way, therefore, is compute first the determinant of a and raise the result to the power 2. This is smart. Instead, doing a times a and then compute the determinant is stupid. Why it's smart? Because we have already computed the determinant of a, so we really have to do no computation. Minus 1, which was the determinant of a computed at point small a, raised to the power 2, which is equal to 1. Then I asked you to compute what? 1 over 2 times the determinant of a times b minus 1. A is a 3 times 3 matrix, b to the minus 1 is a 3 times 3 matrix. Okay, the determinant of b has been computed before, and it was, let me record. B. It was minus 1 times 4, was minus 4. Remember, we computed it at point B. So guys, first of all, you have to ask yourself, does b to the minus 1 exist? Yes, because we computed the determinant of b and was minus 4, was different from 0, so the inverse exists. Does this product exist? Yes, because this is a 3 times 3 matrix, this is a 3 times 3 matrix, so this product is a matrix, square matrix of order 3. So you remember, you can compute the determinant only for square matrices. So look what we do. 1 over 2 is already outside of the determinant, so you don't have to, simply have to copy it because it's outside of the determinant, so copy. Then Binet's theorem tells you the determinant of a product of square matrices, non-singular square matrices, is the product of the determinant. So determinant of A times determinant of B minus 1. So again, determinant of A, but the determinant of B to the minus 1, remember, I had told you before, the determinant of B to the minus 1, the matrix B to the minus 1 is equal to what? To the determinant of B, then the determinant raised to the minus 1. But saying the determinant raised, the result of the determinant raised to the minus 1 is like saying 1 over determinant of B. So the determinant, so in other terms, guys, remember the determinant of B to the minus 1 is the reciprocal of the determinant of B. So 1 over determinant of B. Then substitute, because we have already computed this and this, do the computation, you get 1 over 8. Now, to play again, compute the determinant of 3 times A times 1 over 2 times C minus 1. If one is stupid, it performs all this computation. Otherwise, you can use the property we studied. Okay, no, I'm not saying you're stupid, guys. One stupid, I mean, after having only to say that there is a stupid way to do the exercise and a smart way. So we need to follow the smart way if we can, because this requires several computation if you do not use properties. Remember, here you have a constant, and here also another multiplicative constant. So simply, the first step, I did almost nothing. I simply put them together. Remember that A is a matrix of order 3. C is also a matrix. Does C minus 1 exist? Remember that we computed this determinant before. So C minus 1 exists, and its determinant was, I think, 8. Suppose it was 8 of C, sorry. Since the determinant of C was different from 0, then C minus 1 exists. So this exercise makes sense. Copy. Now remember, so these exist. These exist are both matrices of order 3, so the product exists, so we can really go on. So we can take 3 over 2 outside of the determinant, but 3 over 2 is a multiplicative constant, a constant that multiplies a matrix. Which is the dimension of this matrix? The matrix coming out from the product is a 3 times 3 matrix, so you have to raise it, remember, to the power 3, because this product is a matrix of order 3. So raise the constant to the power 3. Then, Binet theorem, determinant of a product is the product of the determinant. Now, so you see, I copied it, and again, determinant of the inverse is the reciprocal of the determinant of C. Then 3 times 3 times 3 times 3, 7. This is 8. The determinant of A was minus 1. And determinant of C, so I told you bullshit. Determinant of C was equal to 1. Yes, I do not remember. It's above, but I didn't want to check, so it was 1. But you have it in, okay? So do the computation, and this is the determinant. Now, guys, determinant of H to the minus 1 times A transpose. Which was H? Who remember? I can look here. Determinant of H, where is H? I do not remember. Which is H? Let me record. Which was H? The determinant of H was minus 2. 1 times 2 times minus 1, because it was a diagonal. So since the determinant of H is 1 times 2 times minus 1 minus 2 is different from 0 minus 2, so it does make sense. So it's a 3 times 3 matrix, so the inverse of H exists, and they obviously is a 3 times 3 matrix. Okay, so apply Binet theorem, and remember another property. So the Binet theorem, so the determinant of a product is the product of the determinants. And remember, determinant of the inverse is 1 over the determinant of H. Determinant of A transpose, as I told you, first property A is equal to the determinant of A. So you see, I simply wrote it in this way. This is 1 over determinant of H. Determinant of A, simply substitute minus 1 here, minus 2 here, and you get 1 over 2. Here, guys, okay, I can go on because here is essentially the same, guys. There is no different things. Okay, we do this one, which is a little bit longer. So determinant here of the product of these matrices. This is, okay, matrix over. These are all matrices of order 3. We have already told you that this exists. Also, the last one exists because was the determinant, because the determinant of our lower triangular matrix was different from 0. I do not remember the result, but it was different from 0. So the inverse exists. This is a product of matrices of order 3. So you have a matrix at the end, the product is a matrix of order 3. So the stupid way to proceed is the following. Compute the inverse, then make the product of all these 4 matrices, which is a very quite consuming exercise. But if you apply the property of the determinant, you can do it very quickly. Binet theorem, determinant of a product is the product of the determinant. Determinant of A, determinant of G. This is the reciprocal of the determinant of H. This is the reciprocal of the determinant of I hat, okay? Then simply put the result we got previously inside, and you get -1/16. Last question was compute the determinant of A plus B. Well, who cares? What I want to tell you is important is this one. The determinant of a product, if the product is visible, if you are talking about square matrices, etc., thanks to Binet's theorem, is equal to the determinant, to the product of the determinant. The determinant of a sum is not equal to the sum of the determinants. So if you want to compute determinant of A plus B, you cannot do determinant of A plus determinant of B. I never give you this property. I've never given you this property. So what you have to do? Well, do first, okay, guys, please add a, this that means determinant, okay, because I forgot to write it here. Okay, because this is a symbol of determinant, guys. So before computing that, so you see what I did first. First, I need to compute the operation inside the symbol of the determinant, which is simply the sum of these two matrices. The sum obviously is feasible because these and these are both matrices of order 3. So you can sum element by element. So this plus this plus this, etc., etc. You get this matrix. Then you can compute, after having obtained this matrix, that yes, you can compute the determinant. You can develop it along either the line or the row or the line you prefer. However, guys, remember A was 1, 1, 1, matrix A, 1, 0, 1, 0, 1, 1. So simply this matrix, which is plus B, has been obtained by the matrix A by multiplying by 2 the first line of A, by 3 the second row of A, and by 3 the third row of A. So without having to do so many computation, you have simply to do determinant of A plus B, which is this matrix, is equal to what? 2 times 3 times 3 times the determinant of A. Okay, here there was another question, guys. I asked it to compute determinant of A times f to the -1. F to the -1 is the inverse of f. But if you go back, you see that we compute the determinant of f, but at f as a determinant equal to 0. A matrix with 0 determinant is called singular. And when a matrix is singular, that is the determinant is equal to 0, its inverse does not exist. So other very few simple elements since today, guys, are only the exercise. I lost time. Given the, only to review, guys, and then we stop. Given the following matrices, compute the following operation. Trace of 1/2 times L, which is the trace of a matrix, guys, as I told you, is the sum of the diagonal matrix. 1/2 times L means multiply 1/2 L or the elements of L by 1/2. But since I simply asked you to compute the trace. Remember that I told you when you have the trace of a constant times a matrix, take the constant outside. So this operation is 1/2. I wrote everything, so I go. Is okay. I tell you with my words, then I show you. Is 1/2 times the trace of L. Okay, please. When you have the determinant, you have to put the multiplicative constant outside, raised to the power the order of the matrix. If you have the trace, you have only to put it outside, okay? Because, so you have 2 plus 1 is 4, is the trace of L, times 1/2, you get 2. Or maybe let me do it here and then we go below, because I wrote everything, but here I'm faster because we have the matrix here. The trace of D plus L minus U. As you will go below, you will see that this trace, the trace of a sum is the sum of the traces. So you have the trace of D plus the trace of L plus the trace of U. Which is the trace of D? 2 plus 1 is 3, minus 1 is 2. So you have 2 plus, which is the trace of L? 4. So we have 2 plus 4, which is 6. Minus the trace of U. Which is the trace of U? 0. Because you have -1 plus 2 is 0, so is 6. This trace is 6. If you go below, you see. The determinant of 1/2 times D. I repeat, there is everything below, but are very easy, this exercise. Trace of D, determinant of D. Can we compute the determinant? Yes, why? Because it is a square matrix. What kind of matrix is this one? It's a diagonal matrix. So it is immediately the computation of the determinant, because, wait a moment, remember, 1/2 is a multiplicative constant. You can take it outside of the determinant, but which is the order of the matrix? 3. So you have to, don't write, because I repeat, below I wrote everything. Is 1/2 to the power 3 times the determinant of D. But since it is a diagonal matrix, you can compute the determinant immediately as 2 times 1, which is 2, minus 1 is minus 2. So the determinant of D is minus 2, but times 1/8 is minus 1 over 4 if you do the computation. Okay, guys. Determinant of D times L. L. This determinant of this matrix is different from 0. Determinant of D times L. Sorry. D times L. Guys, you have the determinant of the product of two matrices. So you can split it as the determinant of D times the determinant of L. So the determinant of this one was minus 2. Which is the determinant of this one? Is a lower triangular matrix, so you can compute it directly by making the product between the diagonal elements. So this was minus 2, I told you, times 2, so it's minus 4. Boop. Okay, we almost finished, guys. Then I asked, but I think you realize, guys, if you want, okay, determinant of 1/3 times D times 2 times U. So 2/3 can be taken outside. Okay, D and U are both matrices of order 3. 2/3 can be taken outside. And since D times U in a matrix is a matrix of order 3, you have to take 2/3 outside raised to the power 3. Determinant of D times U is determinant of D times determinant of U. So how can you compute the determinant of D? I repeat, diagonal matrix, product of the main diagonal elements, of the elements of the main diagonal. Determinant of U. What kind of matrix is this one, guys? All the elements below the main diagonal are all equal to 0. So this is an upper triangular matrix, and therefore to compute the determinant of this matrix, you have simply to do minus 1 times minus 1, which is 1 times 2. So even without doing additional computation, you understand, 2/3 must be taken outside to the power 3. D is the diagonal matrix, so determinant of D is the product of the diagonal elements. Determinant of U is a lower triangular matrix, no, an upper triangular matrix. So again, the determinant is the product of the diagonal elements. Then here I provided an expression, but determinant, which is the determinant? No, okay, guys, not important. Yes, I think you can stop. Only to tell you guys, which is the determinant of L minus 1? Is 1 over the determinant of L. L is a lower triangular matrix, so the determinant is simply the product of the diagonal elements. So determinant of L minus 1, repeat, determinant of L is 2 times 1 times 2 is 2. Determinant of L minus 1 is 1/2. And without computation instead, how can you develop it? Trace of 1/2D plus 2L will be, l'ho scritto sotto, guardate. Here you have all the steps. Here you have a sum, so you have the trace of a sum is the sum of the traces. Okay, then you can take the multiplicative constant outside of the trace, but you don't have to raise it to any power different from 1. It's 1 to the 1/2. Stop. Trace of D plus 2 trace of L, and then you can do stop here. So guys, we stop here. Guys, we finished the lecture of this course, and I don't remember if it is tomorrow or another day. We need to start the crash course of econometrics. And remember that the crash course of econometrics is at the end of the crash course of econometrics, in particular, before the holiday, Christmas holiday, you will have one test on the crash course of econometrics. For mathematics, you have no crash. For the crash course of mathematics, you have no test. Instead, for the crash course of econometrics, you will have a test.
And if you look at the page of your course of applied econometrics, in particular of Professor Fanelli, you will say that he wrote explicitly that in the final determination of the mark, the result you get in the crash course of econometrics play a role. So even if it's not formally compulsory to take the crash course, the exam of the crash course of econometrics, if you don't take it, professor will take into account that you didn't take it, and so in the evaluation, this fact will have a weight. So, and if you take the exam, my test, the result of my test, better the result you get in my test, better the contribution you have for the determination of the final grade. But for these things, if you have any question, you can ask to the professor of applied econometrics. I simply prepare the exam, I check the test with you, I will check the exam, I will give you the mark in the test, but the professor of econometrics will decide how to weight this exam, I mean the result of the test in the final in determination of the final grade you have to get for the course of applied econometrics. So it's strictly recommended to both take part to the crash course of econometrics and to study, because students very often are already good in mathematics. I'm not saying all, but a lot of students, for a lot of students, this has been, I hope, only a review. But very often in econometrics, people, people very often find econometrics more difficult, even if to me it seems more easy. I mean, the things that I want to explain, but this is due to the fact that few people studied already something about statistics and econometrics. I mean, someone did statistics, but they remember almost nothing. Instead, mathematics, typically you studied mathematics for more than, not only in the bachelor, but maybe previous at high school, etc., etc. So maybe your bases are better. So, okay. So, guys, see you next time. I think tomorrow or the day after tomorrow. But you look at your timetable and you will see. I wrote this morning to Ilaria Tamburini to upload the link, because I created a team room, because the one created by the university wasn't working at all. So I'm sorry for today's lecture that we had to stop 2 times, and I hope in the future will work everything well. Thank you, guys. So I stop here the recording. Thank you, and I hope see you soon. Thank you, Beatrice. Thank you, Beatrice. I stop the recording, and here you find, if you lost past lecture, here inside the